These methods usually require a large amount of training data. However, in the domain of microbiology, the available data is usually limited. So the basic motivation here is to seek methods that will work with a few data. We believe that adding syntactic information or ontology knowledge will be helpful. As a beginning part of my studies, I chose two methods which are based on syntactic features, re-implemented two of them on two datasets. One of them is a kernel-based model called SDP-GA-SVM model, which is originally designed in Maillage, and the other is a neural model, SDP-LSTM model, which is proposed by Xu in 2015 and uses the same syntactic features. This neural model is used as a contrast. As said before, we believe that syntactic information is considered to be useful. Here we make use of a kind of syntactic features obtained from syntactic analysis. Shortest dependency path. Its efficiency has been proved in precedent studies. For a pair of entities, we find the shortest path between them in the dependency graph, and we obtain a sequence in which words are separated by dependency tags. In the experiments, shortest dependency paths are further enriched by other syntactic information, such as number, post-tag, which is a syntactic category, chunk types, entity types, etc. Here I showed an example of representation enriched by number and post-tag. Now I will introduce the kind of methods that is frequently used for relation extraction, kernel methods. Kernel methods convert data from input space to a feature space in which data is easier to classify. And one of the most popular kernel methods is the SVM, support vector machine. Kernel methods can handle non-numeric features as well. For example, shortest dependency path in our case. The key of this kind of methods is to design an effective kernel. Boulescu and Moulet proposed a classical kernel in 2005. The kernel is fairly simple. For two paths that do not share the same length, they are considered totally dissimilar. If they have the same size, their kernel value is the product of number of common elements at each position along the paths. It can be proved that this calculation is equivalent to the dot product. So in their experiments, the kernel function is plugged directly into a SVM classifier. This classical kernel actually ignores the dependency type, but only considers the dependency direction. Here I chose two sentences from a real dataset. We can see that at each position there is only one common attribute. Thus the kernel value is 1. The model that we propose in Maillage is actually inspired by the previous work on kernel-based methods. We propose to use an algorithm, global alignment, to replace the previous kernel. The principle of global alignment is to align two dependency paths and use a normalized score of alignment as their similarity. This algorithm is originally proposed in 1970 to solve the problem of aligning protein sequences. We apply it here in which to capture common subsequences of two shortest dependency paths as much as possible. If two words or two dependencies are not similar, they will be aligned to a gap, which is associated with a gap penalty. For words, we use the weighted sum of similarity of different layers, such as their number, post-tags, as we have seen in the previous slides. global alignment is actually a dynamic programming algorithm. Assume that we want to align x and y. At a certain step for the ith element of x, xi, and the jth element of y, yj, the algorithm needs to decide how to align xi and yj. Therefore, there are three choices. Align them directly, for which the similarity is the sum of score of aligning the part of x before xi and the part of y before yj, plus the similarity of xi and yj. Or we can align xi to a gap, for which the score equals the score of aligning the part of x before xi and the part of y until yj, minus the gap penalty. Calculation for the third choice is similar. The algorithm chooses the way that maximizes the score at each step. The similarity of x and y will be represented by the normalized score of the last step. However, unlike the simple kernel proposed by Bulescu and Moudet, the global alignment kernel does not strictly satisfy Mercer's condition, which means that it cannot be plugged in SVM directly. Thus, it is actually used to encode shortest dependency passes. Assume that we want to transform m passes in the testing set into numeric features, and we have a training set containing n examples. What we do is to calculate the empirical kernel map in which the entry at ith row and jth column is the similarity between the ith example in the testing set and the jth example in the training dataset. The matrix is then sent to a SVM classifier with a standard kernel of our choice. For simplicity, I will refer to this model as SVM model in the rest of my presentation. Another model using shortest dependency passes is used as a contrast to our SVM model. In this model, each pass is separated into several sequences, and each element will be represented by the embeddings. Beside the sequence of word embeddings, there are three more channels, respectively post-tags, dependency, and hyperlink. We initialize the word channel with pre-trained word embeddings. Embeddings of the other three channels are initialized randomly. Here are the extracted four sequences which are not transformed into embeddings yet. For the hyperlink sequence, if the word is a named entity, the hypername is a special symbol entity. Otherwise, the algorithm selects its hypername as the highest level of the well-known lexical resource WordNet. Though we keep the same structure of models as in original papers, implementations are changed according to datasets. We use the BO version of Stanza as a parser, but not the CCG parser used, because Stanza is more recent and proved to outperform its predecessors. Embeddings are not only used in the LSTM model, but also used in the model of SVM, where we use the cosine similarity of word embeddings to measure the similarity of words, which is considered to incorporate semantic knowledge of words, and therefore more accurate. We implemented and tested both SVM and LSTM models on two datasets, Bacteria Biotop BB Rare 2019 and LLL Challenge. For BB Rare 19, there are two types of relations, live-in and exhibits, and it contains nearly 2,000 training examples, which is very few. We can see that the LSTM model obtains a performance slightly worse than the best participant, and it scores 4 points F1 score more than SVM. The best participant actually used another model rather than a kernel-based model. In the dataset of LLL Challenge, the syntactic relations are manually annotated. So for this dataset, I used the provided syntactic dependencies rather than the relations obtained from the standard parser. For LLL, the dataset is much smaller with only 926 examples in total, but among them only 163 positive examples. We can see that on this dataset, the SVM model outperforms LSTM by nearly 50 points and outperforms the best participant as well by 10%. Here, the best participant does not use a kernel-based model either. As a conclusion, though deep learning methods have achieved great performances over many natural language processing tasks, it is still worth investigating classical kernel-based models, especially when the size of corpus is small. In the future, we intend to do more experiments with the same models, but this time with original text sequences between entities, but not their syntactic paths, to demonstrate if the syntactic information is helpful to our model. We will also exploit current state-of-the-art models like BERT and try to figure out a way to combine them with syntactic analysis as already proposed by Rui Antunes and Sergio Matos in their paper in 2019. Thank you for your attention.
Okay, thank you very much for your very interesting presentation. Yeah, you presented to us a quite difficult problem because of the lack of data, and
Yes.
It's very difficult to leverage. So, but you also use which I find very interesting, a similarity score, the GA similarity score. So my question is, with this similarity score, would you think you would be able to use something like clustering methods to do some kind of maybe few-shot learning, something like prototypical networks? I don't know if you've heard of this kind of methods, but it's basically few-shot learning that exploits a similarity score between inputs using some kind of clustering-like method. So I don't know if that's something that you maybe I've tried or not.
Yes, I think it's a interesting. It will be interesting to try, but for now I haven't tried any few-shot learning. We choose global alignment because we want to because we think it is crucial to capture the common subsequences of two syntactic paths, and so we have chosen the algorithm global alignment. In fact, we have used other algorithms to calculate the similarity between paths, but among them we find that global alignment is the best.
Okay. Okay, thank you. Yeah, just what I was saying, that you can, I think, include this global alignment similarity measure into your clustering, so that the sequences would be in the same cluster, easier aligned. But yeah, I think that's a very interesting idea for data set where you don't have a lot of data. So you mentioned integrating syntactic information with so with maybe pre-trained model like BERT.
Yes.
Do you know yet, or you plan to build that kind of integration?
In fact, it's a part of my future work. For currently, I know there exist already several studies on this, and they just use the, for example, they use also the shortest dependency path. And for if we want to use BERT, traditionally we will input the entire text sequence, but here instead of using the entire text sequences, another option is to input the shortest dependency path. So that's all I know for now.
Okay. Okay. Thank you. Thank you very much.